Okay, welcome everyone to this lesson. So we have just a couple of more sessions actually today, and then we were gonna have one more group lesson before paper one. And today I thought about just doing a lesson on thermodynamics because it's a topic that will certainly come up either paper one or paper three, most likely paper one. And I would say a topic that can yield many marks as long as you can avoid the common mistakes and you just recognize where things can go wrong. Okay, so that would be important. And in fact, for today, I thought about a bit more of not of a way a studying lesson, but more of an exam practice. In fact, I've selected questions that are going to be a bit more useful to revise and to learn from. Okay. And if you give me a second, I will just now share the presentation. Okay, so today with this topic of thermodynamics, I want you to remind you that we have these exam prep notes for all of the exam boards, because it's one of these topics that I think can be very easy to study and the exam questions can be very predictable. So to do this, just a reminder that you can really study from these notes, because it's really like kind of exam style questions that come up. And I would like you also to have them open as we start today's practice. Okay, hopefully targeting these exercises that are really the most likely to get wrong, or the most challenging ones. Okay, so if there are no questions, I would say we go right away into exam practice. It's going to be a little bit timed. It's going to be, with a little bit of pressure, just really to train a bit more this exam these exam skills. So if you're watching the recording, I would suggest that you have a timer, because you're going to pause the video, try these questions, 1 minute per mark max. Okay, and then as soon as you play again, it will be me going through the solution or just showing you the mark scheme. Okay, so for everybody, have your exam notes open and let's get started. What I would like you to try also, just as an extra practice, so why don't you write the other like a mini Born-Haber cycle that links a hydration solution and lattice enthalpy, or just like the Hess's triangle, as long as you're able to, to write one of these two can really help in case you ever get stuck with the value. Okay. Okay, so the calculation, first of all, so I want to show you first, like how you can write down how you can write down the diagram, not to show the enthalpy. Take a moment, maybe if you want to pause the video and just see how you write it, but otherwise remember that it's not necessary, Otherwise, you can do also in the triangle form. There are different ways in which you can do the enthalpy of solution. And one could, this type of calculations, one could even be that you just actually remember the equation. And the equation would be, as you can see, lattice enthalpy of solution is. So, and here I would just suggest you to find your way to remember and to learn it, okay? Because the way in which I remember the arrangement of the equation might not be the same as yours. So have a look at the exam notes to get an inspiration of what I mean, and the fact that you can again either remember the type of equation, or you construct the cycle. And the cycle can be in the triangle form or can be in this kind of Born-Haber cycle form. If you got minus 163, you're right. Now, when we think about changes in temperatures and enthalpy, of course, we have to think about equilibrium. So very carefully if you're thinking about something else, because here for the 3 marks, we have solubility decreases. Why? Because of the equilibrium shift. And here you always need to think about the Chatelier principle. Okay, I know here the Le Chatelier principle was a bit hidden in the question, okay, but it's, I think, very important to always relate. So think about changes in temperature and how it relates to the enthalpy. Always mention the shifts and like if there is an increase or decrease in temperature, which reaction it favors. Okay, Very, very important. Okay, we're ready for the next one. It's a 5 marker. Now we're going a lot of marks. Okay. And let's see how we link now feasibility to entropy formation. Okay. Take a moment, 5 minutes all, yeah, to try this because I don't think it's a super straightforward one. Okay, let's go. You want to share with me also actually the approach you're taking to these questions? I think it would be great because it's, I don't think that's simple. But again, just like always, as I say, if you have equations in mind, always write them down because it can really direct either your calculation or your explanation. Okay, I'm reading very good answers here. Again, as soon as you hear feasibility, you know right away that you're going to have to refer to the Gibbs free energy equation. And we know that is all to do with the sign of the delta G. So delta G positive means not feasible. And here I'm really thinking, and again, if you open your exam notes, you're going to have the summary, the summary table with the different signs of enthalpy and entropy, the combinations of them, and when it will depend on temperature or not. What I would like to read also in this 5 mark, it's the like how it's relative to the temperature, okay? Because I mean, it's not written here, but always think about it as independent of the temperature, delta G will always be positive. Again, why? You should have calculated correctly the enthalpy of reaction. So it's just a formation cycle. And then you would notice that the decrease in entropy, and therefore the combination of the sign will always give delta G positive, independent of the temperature. And that's why it's not feasible. Okay, so whoever got the 5 marks, really well done. If not, make sure you make a note of the points that you missed or the misinterpretation. Then let's go with the question number 3. Entropy. So just question. 2 marks, 2 minutes. So of course, here we were looking at the differences in entropy and basically just explaining entropies, okay? And as we know, the physical states that have the highest entropies is going to be the gas. Yeah, very good, we got that. And and also the number of particles, right? So in this case, the gases, mass entropy, and then more atoms, more complexes. So in terms of, careful with the wording that you're using because we're looking at the number of atoms, okay? Because if there are more atoms, then we have a more complex lattice, okay? And this is what we were looking for the 2nd mark, okay? So double check if you really wrote it correctly. Yeah. And otherwise, make a note that with entropy, we have to consider not only the physical state, but also the number of atoms. Okay. Good. Okay, now a little bit of higher pace with the multiple choices. Okay, let's go. 1 minute top for each. And of course, because you're doing exam practice, every multiple choice should help you revisiting a little bit the topic. So make sure that you do a little bit of a more expanded argument. Okay. Okay. Minutes over. Correct answer. It's a C. Whoever got it, well done. If you didn't get it, you need to remember what are the factors that affect the values of lattice enthalpy, which is a charge density, right? Which means that we're looking at the charge and the size, yeah, of the ions. Okay, super. Let's go with the next one. Okay, the minute is over. The correct answer is C. Yeah, the first electron affinity of oxygen. Okay, remember that the electron affinity is the only one in the Born-Haber cycle that it's exothermic. Not the only one because we also have lattice enthalpy, but it's exothermic. Okay, um, because um, because basically it releases energy to gain an electron, right? You're basically kind of making bonds, but is the second electron affinity that is endothermic. Okay, and here it's a very common like question that comes up in Born-Haber cycle that why the second electron affinity is endothermic, and this is to do with the repulsion. Okay, that you're adding an electron to an already negative ion. That's why second electron affinity is always positive value. First electron affinity is a negative value. Make a big note of this if you got it wrong because it's important to understand. Okay, so let's take a minute to correct it. And then whenever you're ready, we can go into question 6. Application to another very important aspect that we mentioned recently. Okay, again, we're looking at the factors that affect the enthalpy, and that would be charge density, so atomic ionic radius. Oh, that's a big mistake, no? If you say atomic radius instead of ionic radius, by the way. So ionic radius and the charge. In fact, that would be B, the correct one, because magnesium, yeah, has the highest, well, compared to sodium and potassium has a higher charge, but compared to calcium has a higher charge density, and then oxygen here, where like it's always the same anion, so um, no comparison there. Okay, good, good, good. Who got it right? Let's go with the next one. I know this can be a bit challenging. Can I see some of your answers in the chat if you haven't wrote it to me? Correct answer is A. Let's think for a moment, okay? So the reason why we have a covalent character, but it's not a fully covalent substance, is the polarization, okay? And that's why A is correct. And it's always the cation that polarizes the anion, okay? And this is what leads to a covalent, or a degree of covalency, okay? Make sure you make a note of this, just in case you don't understand the concept or it's something to revise. But important aspect. And I think in 2023 came up like a very big question to discuss the differences in the values, like theoretical and calculated value, and experimental and theoretical value. And we really need to think about the covalent character. And again, this concept of the charge density that affects the polarization and the size of the anion, which means it's more easily or less easily polarizable. So polarizing power, polarizable is the concept. We see it also in group 2. So if you need to revise the trends of group 2, you need to be able to understand this concept as well, okay? Question 8, more multiple choices. Let's go. Careful with this question because it's, if you studied with me for a long time, you know how I teach the Hess cycle, right? So with this general ABC cycle, which at the end we needed just to find the overall answer. Okay. So take a moment to rethink this because we need to think about, first of all, the good interpretation of each arrow. Again, they has the cycle at the end. We're always just thinking about changing reactant to product and analyze what that is. And here we're looking at the changes in the lattice energy. So what's the definition of lattice enthalpy is, okay, and good who thought about be the correct one, because think about the definition, and here it's so important that you revisit the definition. You really need to think about the definitions, because then you would realize that lattice energy, and in this case, lattice energy, I think AQA has a lattice enthalpy of formation or dissociation. So in that case, it would be specified. But otherwise, lattice enthalpy, it's the gaseous ions to the ionic lattice. And that's why we're looking at the reversed, so minus W. Okay, again, quite a tricky one to interpret. And I hope you got it. And if not, I hope you understand the solution, because I am going fast to other multiple choices. We have still like 3 multiple choices to go. Let's go. So this question, again, is making us think about the factors that affect the lattice enthalpy. And as you can see, different questions, different examples, but we're always looking at the charge density. Again, charge density is affected by what? The ionic radius and the charge. And in this case, we're given both charge and ionic radii, okay? Which means that we're going to have, these are the correct ones. So take a moment to think about it. Calcium oxide, why? Calcium has the highest charge compared to lithium, and oxygen is a higher charge density compared to sulfur, and that's why there is a stronger attraction. Always think about the energy that holds the ions together. And then part B, think about why that is different. The correct answer would be D, because calcium has a higher charge density compared to lithium. As you can see, even though it has a higher ionic radius, it still has a 2+ charge. And also would be because of sulfur, because sulfur has the highest ionic radii, which means that is the most easily polarizable. So remember that the distortion, it would be always caused by the polarizing power of the cation and the ease of polarization, so the polarizability of the anion. The larger the anion, the more easily it is to distort this electron density. And this is what caused the covalent character, and this is what caused the biggest difference in lattice enthalpy. Take a moment to think about this concept. Again, look at your exam prep notes to understand this key concept and see more applications of them. Again, this can be a big open question or small multiple choices, but we're always applying the same concept. Okay, so make sure you make a big note if you got it wrong. If you got it right, well done. And we're going to the next one. Bit of entropy to change it up. Maybe you can add the justification also in your mind. Okay. Entropy somehow is the easiest one, no, to think about. The explanation, as we said before, could be tricky because it's the most obvious is the change in number of particles, the change in physical state, so from solid to gaseous. So this would, of course, be a positive entropy, but also we need to explain it in terms of number of atoms. Yeah, like in this case, so as N we are 4, most atoms, therefore greatest standard entropy. Okay, so hope it makes sense. And now, if you did the Easter course with me, you remember that we did a really fun exercises where we were spotting mistakes. Yeah, because by marking and by recognizing others people's mistake, we can maybe prevent them to do it in the exam. So I would like you to mark this question and tell me how many out of the 3 this is. Okay, if you're watching the recording, pause the video and take your time to do it. This is not really timed anymore because it's more of an interpretation and it's not exam style. It's not exam style. I think it's a great skill to have. So pause the video and play when you're done. I would say 2 out of the 3 because they didn't refer to the elements in their standard states. So you see how easy it is to lose marks in such definitions. So extremely important that you notice every little aspect of the definition. Okay, good, guys. Let's go with the next one. So again, mark it. Is this correct? Is this not correct? What would be, how would you answer it differently? Again, this is the most common mistake. So yeah, ionic radius, atomic radius, careful with that, because if you notice it, you won't make it yourself, or at least you would, as you write down atomic or ionic radius, you would think about these mistakes. Yes, so it's a way to prevent it. Okay, let's go with this one. Cycle. Spot the mistakes if there are. Okay, so no squares here because the arrows, even if they're labeled, yeah, they're in the wrong direction. And the ions in the box are aqueous, but we know they're not aqueous, they are gaseous. Again, here it's so important that you recall the definitions of enthalpies to prevent mistakes like the physical states and so on, okay? Very, very important, okay? Don't make these mistakes yourself, guys. Okay, I hope you spotted this. And yeah, I hope you understand how to write down the cycle. And again, fundamental to recall the definitions, okay? In fact, the most common mistakes for enthalpy of hydration and solution calculations, we have the missing link of ionic size and charge to the enthalpy, okay? But also incorrect equations. Again, these I think are the major things that we needed to think about, okay? We have a couple more questions to go through. Again, really thinking about what can go wrong in these calculations. And of course, we have the specific heat capacity calculation. And let's see where, if there are mistakes in this very nice and tidy answer. it's one thing you should always think about when you finish this type of questions. Guess what? The final sign, exactly. Always remember to double check that, okay? Because when you're calculating the change in temperature, you might not be doing it the correct way around. So you just need to think about the temperature, if it's rising or if it's decreasing, okay? Good. And the division, yeah. The sign and also actually true, the value is divided by 1,000. Oh, that should be okay. Anyway, the biggest mistake is the sign that I always want you to think about. Okay. Second part of this question, and then we have just one more to go. And I like how sometimes they just mix up topics and, you know, like in this case. Would you have given the same answer or different? Anybody? What are you thinking about? One mark, because yes, weak acid, yeah, and I think this is the first thing that should come to your mind when you read neutralization and weak acid, strong acid. But the second mark, yeah, it didn't really explain for how the lower entropy, because again, it's the entropy of neutralization. Okay, so what is entropy of neutralization? Yeah. The entropy change required to, yeah. And if you mention something like it takes energy to fully dissociate, then I think it would still be a mark. Okay, but yeah, for how this explain the lower enthalpy change of neutralization is not addressed. Yeah, it could also be relative to the fact that if it doesn't fully dissociate, it's because it forms less water. Yeah, so less energy released. Okay, so think about again the definitions of the enthalpies. Yeah, and this can really link to the explanation. Okay. And we're now the last one. Of course, we're doing lattice, enthalpy, and just thermodynamic. And you thought that we wouldn't do any Born-Haber cycle? Of course not. There is one, but I don't expect you to do it one right now. But I would like you to identify and correct the two errors in the Born-Haber cycle. And this was actually a past paper question, not like the other questions that were like answers of students. And okay. maybe you want to also give me the final answer, yeah, for this entropy or calculating the enthalpy value that is missing here. Yeah, so make sure you calculate also the missing value and then raise your hand when you're done. Okay. And the calculation, so take a moment to try to calculate the missing enthalpy value, and then we have one more part of this questions that I would like you to do. Okay, in fact, it was the electron affinity that was missing. Yeah, and then yeah, I hope you identified that the enthalpy change of formation, yeah, would be the arrow going down, and then yeah, there is no need to have the enthalpy of atomization. Again, here very important, you recall the definition: enthalpy change of atomization, the enthalpy change when one mole of atom is formed, yeah, either from its solid element or from its atomic atom. Okay, here it depends on the context. Okay, and who got minus 73 was the correct one. It means that you didn't apply the mistakes. And yeah, they're written over here. Okay, and yeah, I wanted you to just think about for a moment here, what is the most common mistakes with the Gibbs free energy? Okay, who is spotting the mistakes that I never ever wanted to make in such a simple calculation? So the sign of your delta G, it's negative and is correct in this case. So we should always think about the correct math. But the most common mistake that can come up is forgetting the units. And come on, they are written right there on the screen. It's extremely important that you notice them, okay? Because you always have them here. So it's a mistake that it's not allowed to be made because the units are there. And you see that kilojoules and joules, of course, so you're gonna have to change the entropy into kilojoules as well. Okay, good. And then yeah, in terms of the feasibility, we in this case is correct because it's negatives, but it's just the value that is wrong. Again, units is extremely important. Okay. And I think that's okay. I wanted just to think about one moment and to finish off the common mistakes with the Born habit cycle. Okay, always think about the like how you write down the equations. So if you're forgetting electrons, like ionization, electron affinity, so there are always some like in here we didn't construct any Born-Haber cycle in this lesson, but just remember we need to be very meticulous in how we write the equation. Okay, always think about the ratios and state symbols. How you rearrange it, again, you either remember the equation to calculate it, like lattice enthalpy, and then you just rearrange it, or you use the Born-Haber cycle, just like we always do for the ABC cycle to calculate, to find the correct overall equation. And then one very important thing, we didn't see examples there, but you have this example in your exam notes. If you use two vague terms, so bigger and smaller means nothing when you're talking about exothermic or endothermic values. So you always need to mention more exothermic, more endothermic, okay? And then again, we saw this concept of ionic radius, atomic radius. So please don't make these mistakes as well, okay? And then the final is that the common mistakes with Gibbs free energy. Of course, we've just seen one, forgetting to convert the entropy. Again, this is not allowed because the units are right there. So please highlight the units when you come across these exercises. And then I think all of you interpret really well the signs of delta S. So I hope it's okay. Just one last thing that I wanted to say is that the common calculation that come up is setting the delta G as 0 when you're calculating the temperature feasibility. In fact, as you can see, like in this question, the second part is calculate the temperature at which delta G is equal to 0. This is super simple in terms of calculation, but again, this is also asked as what is the temperature when the reaction becomes feasible, or calculate the minimum temperature, or calculate the temperature. And here, of course, we need to set delta G at 0 because that's kind of the turning point for being spontaneous and not spontaneous. Okay, so please, guys, take a moment to look at the common mistakes listed in this lesson. Also, the exam notes. I think you have all of the possible mistakes and the possible exam questions that can come up in this topic. Again, a very high yield topic. Yeah, that if you don't make these mistakes, I'm sure that all of you can get 100% of the marks on. Okay, so I hope today you got the chance to make a note of the little mistakes to avoid in case you made them yourself. If you didn't, just well done. And because you're so close to paper one, if you feel like you just did super great in this topic, then that's it. Yeah, maybe revise it just if you come across any of these questions in past papers, but otherwise just trust what you've learned so far. Okay, so thank you very much everyone for joining. And if you have any questions, always let me know.